So in this video, I'm going to do just a quick overview of complex numbers. I have a lot of other videos on complex numbers. If you need to go back and look at some of those, or just let me know if anything I do is confusing. But basically, we're going to start with the basic definition of complex numbers, and we're going to go all the way through what it means to do powers and roots and things like that. So it's going to be kind of fast, but let me know if there's anything you want me to go over in more detail. I'm happy to do that. So here's the basic idea. Sometimes when you're solving a math problem, you have no solution. For example, if you are a little kid and I asked you, what is 5 minus 7? You would say, I can't do 5 minus 7 because you're always thinking in terms of concrete things. If you got 5 apples, you take away 7 apples, can't do it. And that's a perfectly reasonable response. It turns out, however, that if we start considering what if there was a number that was the solution, we can do interesting things with those numbers. So we start thinking about things like negative numbers. Negative 2 is a perfectly reasonable response to that. It's just saying 2 steps to the left on the number line. Similarly, if you're a little kid and I asked you to do 8 divided by 3, you might say 3 doesn't go into 8. But it's a perfectly reasonable thing to say, well, okay, what if it does? 3 goes into 8 2 times with a 2/3 remainder. And you start realizing that that fills in a lot of the gaps on the number line. There's still an infinite number of gaps to questions like, what's the square root of 5? Well, the square root of 5 is just another number that fills in that gap. And you'll see that with thinking of basically these questions of what are the answers to addition and subtraction, what are the answers to multiplication and division, and what are the answers to powers and roots, you can fill in all of the points on the real number line. So what is the square root of 5? It's 2-ish. With all of those, we can fill in all the numbers on the number line. Then you get to a point where you try to solve a problem like this. X squared equals -1. And you say, there is no number that squares to equal -1. A negative times itself is a positive. Positive times itself is a positive. No number times itself is a negative. Just like we've done with subtraction reaching negative numbers, just like we've done with division creating fractions, just like we did with square roots creating some of the irrational numbers, we now have a new thing that we're doing. We're just saying x is equal to a new imaginary number. Just like when we took square roots, we got a positive and a negative number. Here we get a positive and a negative number. The next question that comes up naturally, though, is how do I represent that visually? All of these answers over here fit on a number line, left and right like this. So we can't do anywhere on the number line. All of those spaces are already taken up by an answer to a previous question. So we don't worry about it. We just tack on another number line orthogonal to the previous one, meaning just perpendicular. Orthogonal is just a fancy word. Where do we put them? Here's where we put the number I. Here's where we put the number -I. And with this, we have opened up an entire new dimension of numbers. We can now answer questions like, what if we had x plus 3 squared equals -4? We can solve that by taking the square root of -4. Well, the square root of 4 is 2, so square root of -4 is 2i. The other square root is -2i. And if we solve for x by subtracting 3, we get -3 plus or minus 2i. That has a real part, and it has an imaginary part. The real part functions just like your x value on an xy plane. So we go 3 steps left and 2 steps up for the imaginary part. The point -3, 2 is equivalent to the number -3 plus 2i. There's also the buddy point down here, -3 minus 2i. So that's the very basic idea of what we're doing is we're solving problems involving square roots of negative numbers, and then we're representing those answers as points on the plane. Okay, so I'm going to clear the screen. We're going to move a little on from that. What we've established so far is that if you have a number, x plus y I, we can represent that as x comma y. Now, what I want you to think about is there another way that we can represent these numbers? So, for example, if I have a point like this one right here, I'm going to think of it as the endpoint of a vector. We just finished up talking about vectors. This is the point 2 plus 2i. But another way that I can come up with representation of a vector is based on the angle that that vector makes with the x-axis here and with the length of that vector. And if you do that, you'll notice our best friend, a right triangle, shows up. Everything is always triangles here. So if I think about the hypotenuse there, I can go 2 squared plus 2 squared equals r squared. We usually use the letter r to stand for the distance from the origin, kind of like a radius from the center of a circle. And so I get here 8 equals r squared, or r equals the square root of 8. Okay. You could also, if you like to simplify your square roots, call it 2 root 2. It's totally not necessary. To find the theta value, you can remember that tangent of theta is opposite over adjacent. So theta is just the arc tan of 1, which is in pi over 4, or you can call it 45 degrees. Or if you're someone who loves tau, you can represent that in terms of tau. So what we end up with is that our complex number 2 plus 2i is also able to be represented in terms of r and theta. And so we can call it the adjacent value here is x, the opposite value is y. I know that cosine of theta is equal to adjacent over hypotenuse, which I'm using the letter r for. And sine of theta is equal to opposite over hypotenuse. In other words, r cosine theta is x, and r sine theta is y. So we could write our complex number 2 plus 2i as 2 root 2 cosine of pi over 4 plus, sorry, I'm squeezing it in, 2 root 2 sine of pi over 4. Now you might be wondering, that is great, but that seems like more writing than 2 plus 2i. And you're right. There's a shorthand that people use, which is instead of writing cosine, oops, I should have put an I on there. I, because the y value has an I on it. So we have cosine 2 root 2 cosine pi over 4 plus 2 root 2 I sine of pi over 4. So there's a shorthand here because cosine and sine are always going to be related to the same theta. The shorthand is to write it as 2 root 2 using CIS pi over 4. And CIS just stands for cosine plus I sine. And so now it's okay, it's more or less, it's about the same amount of writing as writing 2 plus 2i. So what we have is a separate representation of our complex numbers. X plus yi is equal to r CIS of theta, remembering that r is the square root of x squared plus y squared, and theta is the arctan of y over x. But I'm going to put a little asterisk there because you have to be careful about making sure that your theta is in the correct quadrant right there. And so sometimes arctan will give you the angle that's on the right half of the y-axis, and you need to use adding 180 degrees, adding pi to it to get the angle on the left half. So just watch out for that. Arctan will always give you angles on the right half of the coordinate plane, so you might have to add pi, to add 180 degrees to get the angle you actually care about. So just be careful there. So now you still might be wondering, okay, the CIS is a cute abbreviation. Why is this useful? So what I want to show you is what happens if I take 2 plus 2i, and I square it. Well, 2 plus 2i squared means I take 2 copies of 2 plus 2i, and you multiply everything out. 2 times 2, 2 times 2i, another 2 times 2i, and then 2i times 2i makes 4i squared. If you remember a few minutes ago, I talked about how I came about from being the square root of a negative number, right? I is the square root of negative 1. And that's equivalent to saying I squared is negative 1. So that means what we've resulted in is 4 plus 8i minus 4, because 4i squared becomes 4 negative 1s. So now I just have 8i. What this means is my dot is going to be right up there at the very top of the screen. Well, what happened to my complex number? Well, two things changed. My old theta was 45 degrees, and my new theta is 90 degrees. My old r was the square root of 8. My new r is 8. Okay, so there were two things that happened here. My old theta got switched into 2 times theta. My old r got switched into r squared right there. It's not obvious that 2 plus 2i squared would transform into 8i, but these conjectures down here are a lot more obvious of something that would happen. Okay? So it actually turns out that this is a true statement in general. So what I'm going to do is do a quick proof of that true statement, flip it around to talk about roots, and then we will finish with this video before it gets way too long. Again, this is just a quick overview. I encourage you to let me know what part is confusing, or parts, I guess. So what I want to look at is our general situation of, we just said that x plus iy can be written as r cosine theta plus I sine theta, I sine theta. What I want you to notice is the r value can be factored out to leave us with the cosine theta plus I sine theta, like that. So it kind of makes sense that I can think about what happens to the r values separately from how I think about what happens to the theta values. So what I'm going to do next is I'm going to take my complex number and I'm going to raise it to the nth power. If you raise it to the nth power, then we can see the first part of our conjecture is pretty immediately true. The r value just gets raised to the nth value right there. Okay? So this is a very useful thing, that if you raise a complex number to a power, then the distance from the origin gets raised to the same power. Now, the other part of the claim that I want to show you is why, I missed a theta, why this part here becomes multiplication of the angle. Okay? And so the way that you can do this is by using our good old friend, the binomial theorem. So let's look at what happens when we do cosine theta plus I sine theta to the nth power. What we end up with is cosine to the nth theta plus n choose 1 cosine to the n minus 1 I sine theta plus n choose 2 cosine of n minus 2 of theta, I sine theta squared, etc., 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 all the way up to I sine theta to the nth power. What's going to end up happening is you're going to have alternating powers. You're going to have every other term will be real and imaginary. So you'll have an alternating thing: real, imaginary, real, imaginary, real, imaginary. Because when you raise I to an even number, it's going to cancel out. When you raise I to an odd number, it's going to still be there in the answer. So we have cosine n theta, and I'm going to skip over and choose 2 cosine n minus 2 theta. I squared sine theta becomes a negative. So I go negative sine squared theta. Then I have plus n choose 4 cosine of n minus 2 theta, n minus 4 theta, sine to the 4 theta, all the way up there, plus all of these I values. Let's see if we can make this work out. Now the I values are multiplied by n choose 1 cosine n minus 1 theta, sine of theta, plus n choose 3 cosine of n minus 3 theta, sine of theta. Oh, that one should have a negative on it. Okay, so what I'm thinking is that I might need to make a separate video just focusing on this idea here, because this is going to get a little long to make all the details work out. I don't want to get bogged down in the details of this. So I'll make a separate video on this idea here. But basically, you'll have to take my word for it on this part. What ends up happening is each of the sine squareds can combine with the cosines there in a very nice way to cancel a lot of things out. And similarly on this, each of these sine cubes and sine to the fifths can cancel out with the other terms. And again, I'll make a video going more into detail. I just don't want to get too bogged down here. We end up with cosine of n theta plus I sine of n theta. And you can see that if you look at your double angle identity, your angle addition identity, and your for sine and for cosine, you can see how that might work out. Again, I may be bit off a little more than I wanted to chew in this video, but the point is that that's where you're going to end up. So the last thing I'll mention is that you can use this same idea to find roots. So the idea I'm talking about is that if you have x plus iy to the nth power, you can think of that as r to the n cosine plus I sine of n theta. If I wanted to take, say, the nth root of something, I can use basically the same idea, r to the 1 over n cosine plus I sine of 1 over n theta. But the tricky thing here is that you actually can find multiple roots. Like with a square root, you can find 2 different roots to it. With a cube root, there's 3 different answers to it. With a fourth root, there's 4 different answers to it. And the way you get those other answers is you add full circles on. So a lot of times we'll write 2 pi k like this. So again, kind of ambitious to fit that much in the video. Comment on what doesn't make sense. I will definitely make some other videos breaking down some of those proofs in a little more detail. And also check out some of the other videos I've made on complex numbers, because they go over a lot more examples of this sort of thing. So I'll call it good for there.